Hey y'all, today we're going to be looking at Hess's law as it pertains to equilibrium. Now in the past we looked at Hess's law in thermochemistry, and in thermochemistry the key to Hess's law was that delta H, delta S, and delta G were all state functions. So we used Hess's law to go from different elementary reactions to identify the delta H, delta G, or delta S of a target reaction. And the way we could do this with thermochemistry was by manipulating the elementary reactions to make sure the stoichiometric reaction equals the target, and then using our delta H values or delta G values or delta S values of those elementary reactions to determine the delta G, delta H, or delta S of the target. With equilibrium, the thing to keep in mind is that we're dealing with K values, not the thermodynamic properties. And because we're dealing with K values, we need to understand how K pertains to a reaction itself. So the K value, remember, is products over reactants. And each product and reactant is raised to the power of its coefficient within our equilibrium constant. So when we're looking at elementary steps, each elementary step has its own K value. We're now going to use that understanding of K values for each elementary step to find the overall K value for a target reaction. So let's take a look at how this works. There are a few rules with Hess's law as it pertains to equilibrium. The first is if we reverse a reaction, what we're doing is we're flipping the reactants and the products. Now, if we think about this in terms of a K value, what we've done by flipping reactants and products is taken the reciprocal of that K value. So what was K would now become 1 over K, or K to the negative 1 power. The second rule of equilibrium as it pertains to Hess's law is that when you multiply coefficients in a reaction by a certain value, let's call it X, then what we're going to do is we're going to multiply the exponents in the equilibrium expression by the same value X. What this really means is that we are going to raise the K value to the power of X, the coefficient multiple in the original elementary step. For example, if I cut all the stoichiometric values, the coefficients of an elementary step in half, I'm going to take the square root of the elementary step's K value. Simultaneously, if I'm going to double the coefficients in an elementary step, I'm going to square that elementary step's K value. Finally, if you remember Hess's law in thermochemistry, to find the overall delta H, delta G, or delta S of a reaction of a target, we add together the delta H's, delta S's, or delta G's of the elementary steps. In equilibrium, we're going to do it a little bit differently. In equilibrium, to find the K of the overall reaction, we're going to multiply the K values of all of the elementary steps. All right, let's take a look at a practice problem. Here I have a target reaction, and I need to find the K value of that target. In order to do so, I'm given 2 elementary steps and the K values of each of those 2 elementary steps. So what I'm going to do in summary is first manipulate this elementary steps in order to match the stoichiometry of the target, and then use the K values of those manipulated elementary steps to find the K value of the overall reaction. Let's go ahead and do this. First thing to note is that the NH3 in the target is a reactant. But in my first elementary step, the NH3 is a product. So I need to get the ammonia on the reactant side of the elementary step. In order to do this, I reverse the first elementary step. The stoichiometry of the NH3, of the ammonia, in that elementary step is 2, and the coefficient in the target is also 2. So I don't need to manipulate the coefficient at all. So all I'm going to do is take the reciprocal of the K value. And the reason is because, again, all I did was I flipped the reaction. Now, when I look at the second elementary step, I notice that the HI and the I2 are off by a factor of 3. I need to multiply that second elementary step by 3 in order to match the stoichiometry of my target. When I do that, I'm going to cube the K value of that elementary step. In doing so, I'm going to double check the stoichiometry matches. The H2's cancel. The HI, the I2, and the NH3 all match in terms of stoichiometry of elementary steps and the stoichiometry of the target. And so now all I need to do is I need to take those new manipulated K values of the elementary steps and I multiply them together. This means that my K value of the target reaction is going to equal 2.5 times 10 to the fifth. Remember, K values don't have units, so that's a naked number. 2.5 times 10 to the negative fifth is, or times 10 to the positive fifth is my answer. All right, so now you've seen me do one. How about you do one? Here I'm going to give you a slightly more challenging Hess's Law problem because now it involves 3 elementary steps. I want you to manipulate the 3 elementary steps to match the target reaction here, and I want you to find the K value of that target. Take a few seconds, pause the video, do the problem. When you're done, come back and we'll talk about it. All right. Did you get 7.4 times 10 to the negative 24th? All right, if you did, you're right. Here's why. What we had to do to manipulate these 3 elementary steps was first do nothing to the first elementary step. The reason we did nothing to the first elementary step is because the nitrogen is already on the reactant side and its coefficient is just the same as it is in the target. The second elementary step we had to reverse. And the reason for that is because the NOCl was on the wrong side. So we needed to flip it. But the coefficients were all right. So all we needed to do to that K value was take the reciprocal. The third elementary step, all the reactants and products were on the right side, but the coefficients weren't. We needed to divide all the coefficients by 2. Now, when we divided all the coefficients by 2, we take the square root of that K value. To verify that all of those elementary steps stoichiometrically match the target, we make sure we cancel all of the things that are the same on opposite sides, and we combine things that are the same on the same side. We see that this matches our target. Therefore, the K value of our target is equal to the multiplication of K of the first, K of the second, and K of the third. Therefore, the answer we get is 7.5 times 10 to the negative 24th power. All right, so that wraps up today's video. Today, we looked at Hess's Law as it pertains to equilibrium, which is a little bit different than the Hess's Law that we looked at with thermochemistry. Remember that Hess's Law of equilibrium is fundamentally about the equilibrium constants. Because it's about the equilibrium constants, which are based on the mass action law, products over reactants raised to the value of the coefficient, the way we manipulate the elementary steps will change how the K value looks for the target. Also, remember when we're reaching a target K value, we are going to multiply together the K values of our elementary steps. This video was written, directed, and produced by Drew Goldkamp and Tyler Dong. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.